x del x, del x del by x, this Lagrangian, del mu. In this case, the current del x is itself J. And all its modes, you know, all the various descendants, I mean, all the various J minus n's of this, so various other derivatives on del x give you all that. So this is an example. Okay, the point here is this, that in 2 dimensions, when you have a global symmetry, that tells you that del z bar jz plus del z jz bar is equal to 0. That is conservation. Now there are 2 ways in which this equation can be obeyed. The most generic way is if del z jz bar is not 0, del z bar jz is not 0, but the 2 cancel each other. But there's another way, a sort of simpler way in which it can be obeyed. If del z bar jz is equal to 0 and del z jz bar is equal to 0, often just jz bar is 0. In the case where just jz bar is 0, the current conservation equation becomes del z bar jz equals 0. So you have holomorphicity, and once you have holomorphicity, all the various Fourier modes are also conserved just because they're holomorphic. You take z to the power n times jz, that is also conserved just from holomorphicity. Okay, so you get many conservations free in 2 dimensions in the situations in which you have holomorphicity. And of course, all this is just blah blah blah. The point is that there are interesting physical situations in which this happens. One of which is this Wessel-Minowitten theory. We will discuss Wessel-Minowitten theories in great detail. We discussed it briefly for SU2. We will discuss them in more detail as we go on. I will show you just classically how the holomorphicity comes about, because of cancellation between the kinetic term and the Wessel-Minowitten term. Okay, so we'll discuss all of this. But the point here, it's an important question, it's not a gauge symmetry. If it was a gauge symmetry, states would not transform into representations of it. It would be annihilated by it. Okay?
But can you see it simply, like what kind of symmetry is it? Is it something on the group manifold? I don't know. What kind of thing it is? This correct symmetry?
This current symmetry. Right. What kind of thing is it? Kind of thing is it? The thing is this, that you've got a group valued symmetry, Lie algebra valued symmetry current, one for each Fourier mode on the string. Right, so we've got a field theory. Field theory lives on a spatial circle. We're very used to the fact that if you take the current, the J0 component of the current, and integrate over space, that gives you a conserved current. If you had a Lie algebra varied symmetry, you'd get a Lie algebra valued conserved charge. This point we're used to. The point here is that not just the integral over the circle, but the integral with an additional z to the power n is also conserved. So your intuition is correct. It's going towards saying that it's not just a current that is conserved, not just a charge that's conserved, but a more local version of that.
Different modes.
Different modes are also conserved. Okay, but
kind of some moments.
It's like moments, exactly.
Yeah, so Loga once told me that it is some sort of a moment.
Yeah, because it's just z to the power n, and z to the power n on the circle is e to the power n theta. Right, so all the modes of those are also conserved. Right, you understand why z to the power n is I n theta, right? Because we're on the plane, we take the circle. So the various Fourier modes on this current are also conserved. Yeah, it's an amazing thing. You know, it doesn't happen usually in any interesting situation in a higher dimension. The higher dimensional analog would be, let's say, in a 3-dimensional field theory, would be having the theory on S2 and having all spherical harmonic modes of something being conserved. This kind of thing doesn't usually happen. Now, it's not so different from having Virasoro symmetry. In Virasoro symmetry also, the various ln's were the various Fourier modes of the stress tensor. It's like that, but just with Lie algebra. Okay? Okay.
It's analogous to like Ln acting on those physical states being zero.
It's ln acting on physical states being 0, but more importantly, it's the L minus n's acting on physical states, transforming in representations. They form the module, right. That this, I mean, if it had been everything acting on it equals 0, that would have been a gate symmetry. That some things act on it give you non-zero, that's what's important. Okay, excellent. Let's continue. So in today's lecture, we want to remind ourselves of the Sugawara construction. Okay, we want to remind ourselves of the Sugawara construction, but this time for a more general gauge theory than SU2. Okay, so you remember what we had done, right? What we had done for SU2, and we're going to, let me go to this board. What we've done for SU2, and we're going to try to do the same thing here, is take JA of Z, Z1, JA of Z2, and then take the limit Z1 goes to Z2, sum over A. We want the group invariant thing, right? And then take the limit Z1 goes to Z2 to try to produce an object. Okay? Our stress tensor is going to be proportional to this object. You remember this from our SU2 construction. Okay? And you remember also from SU2 that it was a little delicate to understand the OPs of this object with, let's say, a primary operator. Okay? So consider a primary operator phi, which is Z3. Okay? This phi is in some representation. So let's say this phi is in some representation R. Okay? And by definition, JA on phi R, let's say Z and W, is equal to the group generator matrix in representation R. Okay? And then there is some multiplicity label. So we have Ij phi j of W divided by Z minus W. This is how J's act on primary fields in some representation. This we're familiar with. Now we want to know if we take these two guys, take J1 to J2, and then act on these fields, what do we get? It's very tempting to try to do the OP one by one, but that's not correct, as you remember. The reason that's not correct is that we are going to be interested in the limit Z1 goes to Z2. So in insertion space, we have 1, 2, and let's say 3. We're first taking 1 to 2, then taking 3 near these other guys. So 1 will always be closer to 2 than 3. And you're not allowed to use OP. You're not allowed to use OP between 1 and 3 and 2 and 3. You're not allowed to use, for instance, OP between 1 and 3 if 2 is nearer to 1 than 3 is. Right? The rule, if you remember, was can you enclose this in a circle that contains only 1 and 3 but not 2? And when 2 is separated by any finite distance, it's always possible. You can always find a funny circle where you can do that. But if you've taken the limit first, it's not separated by finite distance. So you cannot do it.
So after expanding, you keep them.
Exactly. So the idea was this. You first, what we do is to just look at the whole thing with separated points, Z1, Z2, Z3, and look at the analytic structure of the whole correlator. You know, there could have been other things, but we look at the analytic structure of the whole correlator. Okay? So what we want in particular is to look for all singularities as either 1 goes to 3 or 2 goes to 3. Any term that is singular when either 1 goes to 3 or 2 goes to 3, we want to keep. When everything is separated, it's clear what's happening. Those singularities are, of course, recorded by the 1 goes to 3 OP and the 2 goes to 3 OP. Okay, so this quantity, I've got 1, 2, 3 all separate. How does it look? It goes like JA of Z2 times, now let's be careful, Z1 minus Z2 TA R, let's put some indices here. Let's suppose this was I. TAR IJ phi j R. Sorry, this was Z minus Z3. Yeah, phi j R at Z3. Okay? That's the term that is singular when 3 goes to 1. But there's also a term which is JA Z1 by Z2 minus Z3 times TAR IJ phi j R Z3. Okay?
Can I think of this like this? I have point 1, 2, 3.
Yeah.
I do the Common transformation, so I bring 3 in between like 1 and 2, and then I'm doing the.
Yeah, you can do that. You can think of it. You can always, you see, if I've got 1, 2, 3, unless this guy is in a straight line, unless 1, 2, 3 are in a straight line, you would always find a circle that encloses 1 and 3 but excludes 2. Suppose 2 is just here. You'll be able to find a circle like this. And then this thing is analytic. Right? So you get the singularity in that way and then analytically continue. Even to that one point if you are interested in that one point. Okay? So at generic points you can find a circle that does this. So you can always write this down. Is this clear? Okay, great. Now we've got this written down here. And we now, after having taken this OP, we want to do this expansion. That is, now we want to take the limit 1 goes to 2. Okay? So we want to take the limit 1 goes to 2. So let's see. And by the way, we were interested not in okay. We were interested in looking at we know that in the limit 1 goes to 2, we know that in the limit 1 goes to 2, we're going to get a singularity from j goes to j. Okay? So we will remove that singularity. So what the kind of the thing that we're going to define as JA minus k by Z12, the whole thing squared. This will be our eventual, proportional to this will be our eventual definition of the stress tensor.
K times the dimension.
Dimension of the group, correct, times dim.
If A is sum.
Yeah, if A is summed off. Correct. That's correct.
And the second term in the OP is dropped because A is summed over and FABC is antisymmetric, is it?
That's correct. That's correct. That's correct.
Second term.
Yes, second term is off. No other singularity because we've got A with A. Not even the sum is needed, just that it's FAA. Anything symmetric goes away.
This is normal ordered operator.
This is our definition of normal ordering.
So you subtract all the singular
You subtract the thing that becomes singular as 1 goes to 2.
at 1.
As 1 goes to 2. Okay. So we've got this expression here. So we were looking at that 3-point function. This was every term that was singular as 3 went to 1 or 3 went to 2. Okay? And now what we do is to take G. Okay, this is some complicated thing. Okay, let me work. Yeah, let me work it out. I was doing it for a primary operator. Pulchinski does it for a current itself. Let me do it for that. So let me just imitate his. Actually, it will be the same thing. Okay, let me just continue this. What? Say again?
In this OP expansion,
Uh-huh.
maybe you should have taken Z2 to Z1, right? Not Z1 to Z2. Because he wants to see the similarity between Z1 and Z2.
Sorry, we want to see the singularity between.
Z1 and Z2.
No, we're not interested in the singularity between Z1 and Z2, right? We want that is removed. We're interested in the singularity between T and a primary operator.
We know the singularity between Z1 and Z2.
Z1 and Z2, exactly. We want to check what happens when this composite object becomes near to Z3, right? Okay, right. So okay, so let's just continue with this exercise. Okay. Now what we do is to take the limit Z2 goes to Z1. Okay, so we take the limit Z2 goes to Z1. So let's see. In this limit, this was Z2 goes to Z1. Yeah, this actually, so, 1 minute please. 1 minute please. Am I getting confused? Just a second. Just 1 second please. Yeah, this is actually completely straightforward. This part will come completely straightforwardly. So we take the limit Z2 goes to Z1. Here we just set, we're only interested in the poles. Here we just said 2 is equal to 1. Here we also set just 2 is equal to 1. And so we get T, and then we take the limit Z2 to Z1. Just a minute.
You should have seen J-like contribution in the right? Because you would expect that this stress tensor leaves phi right behind, right? It does not transform in that representation.
No, but we should see its scaling dimension.
I mean, yeah, up to some scale, it should be proportional to phi.
Oh yeah. What we should get is a TT. Just a minute. So I'm getting confused about the fact that we've taken. Just 1 minute. I suppose now we once again take the OP of this with this. Yeah, exactly. Now we once again take 2 to 1. Am I getting the right answer? Just 1 second. Just 1 second. Just give me 1 minute. Let's see what Pulchinski has done. I may be messing up. Just 1 minute. Yeah. Give me 1 minute. I think good. So let me do it this way. Let me take. I see. What he wanted was never having a 3 in here. Okay. 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 Yeah, he wanted a 1 in there. And
You would take Z3 to Z1, not Z1 to Z1.
3 completely comes in this coefficient, right? This singular
give me one. I suppose with a primary, the difference is that you just Taylor expand, right? Okay, fine. Yeah. So this is okay. You see, Spulczynski did it with 3 currents. So you could take one with J was JJ. Here, what we know is the Taylor expansion of J with a T, as we take J to T, J to a primary, but now we can just Taylor expand. Okay, so what we will do now, let's do it carefully. So we will now take this Z3 and Taylor expand in Z3 minus whichever we want. Let's say Z1. Okay, so this is JA, Z2, TARI times phi AR Z1 plus Z3 minus Z1 phi, what this is phi J, this was TAIJ, phi J of del Z, phi J of R of Z1 into Z3. Yeah, I've got Z3. Right. So we will have this, the whole thing divided by Z1 minus Z3, plus we will have a similar term on the other side. Let's write that down. That is JAZ. This was 2. That was JAZ1 by Z2 minus Z3 into TARIJ phi J of R Z1, let's say. No, let's Z2. This time we'll do 2. Okay, plus phi J of R into del Z, Z2 into Z3 minus Z2. This whole thing is divided by Z2 minus Z3. These extra terms are non-singular, unless I suppose they're non-singular. Wait, but we'll be careful because now we will get another 2 goes to 1 OP, and that might kill. Let's just be careful. Yeah, perhaps in this case it will be non-singular. In some cases it will turn out that will cancel some higher singularity. Maybe that's only in the case of J's because there's a 1 by Z square singular. But let's just be careful. Yeah, the extra terms so far look non-singular. Maybe they just don't do anything. I think you're right because we're not going to get a del Z in the end. Okay, yeah, but just let me do it carefully. Okay, so we have this. Okay. Now, we have this object.
There is also the minus sign, minus of the expectation, like the infinite part that you cancel out.
Yeah, but the OP of that with phi is 0. It's just an identity, so that's not playing a role here. Yeah. Okay, excellent. So now what we do is we take 2 to 1 in that one and 1 to 2 in this one, or 2 to 1 in this one. Yeah. Okay, so let's take 2 to 1 in that one. So now we get this extra term which is TAR, that was IJ. Then we get TAR, and then we'll get some JM phi MR Z1, and now this whole thing had a Z1 minus Z3, and we get a Z2 minus Z3. Z2 minus Z1. Z2 minus Z1. Okay, we get this term. Okay, plus something similar plus something similar. It's just that we've got this extra z3 minus z1. Okay, so this term, this thing will be sort of common. We'll get z3 minus z1 times del z. So del of what we get when we take this 2 to 1. So we will get a del of 1 over z2 minus z1 times z3 minus z1, right? There will be a phi. Oh, wait, this del is, sorry, I'm so sorry. Yeah, this del was acting, and then, yeah, so just let's be careful. This del z was acting on phi, and then what we got, okay, so let's just do it carefully. So that is del z1 of phi of z1 divided by z2 minus z1. Right, now I think it's right.
Then that factor won't be there, z2 minus z1 for the second term in the denominator.
z2 minus z1. You're right. So this is divided by z2 minus z1. And now it's right. Okay. And we get a second term which is t. One is replaced. 2 and 1 are exchanged with each other. And I suppose that's just it, right? Because here we had yeah, how could it be anything else? 2 and 1 are replaced by that. Plus TAR IJ TAR JM phi MR Z2 divided by Z1 minus Z2 plus Z3 minus Z1 del Z2 phi of Z2 divided by Z1 minus Z2. And this whole thing was divided by Z2 minus Z3. Okay. And now we want to take the limit 1 goes to 2. Okay. Now we want to take the limit 1 goes to 2. So let's see. That's right. So let's see. So the phi term becomes, let's see. Oh, we do want the del z because that should be the yeah. Okay, good. So let's first gather the 1 by z square singularities. Okay. So what we'll get is t squared. So TA acting like a matrix. I'm not writing the indices. TA on phi of Z1. Z1 was the insertion point, let's say, of, okay, now we were the insertion point, okay, the TA of Z, so we've taken the 2 to 1. Let's say we've taken Z2 goes to Z1. I'm doing the calculation very badly, I apologize for it. If I'd done it before, I could have organized it better. Okay. Okay, because eventually now we'll have to again expand this in Z3. Yeah, I'm sorry, but let's just see what we have. Okay, we have Z1 minus Z3, the whole thing squared. I'm just taking the most singular term. Okay, so we have this guy and a similar term on the other side, or maybe with a 2, plus okay, plus TA by Z2 minus Z3, the whole thing squared, phi of Z2. Is this correct that this is one of the terms?
No, I think this Z1 minus Z2 will common, and after taking this Z1 minus one Z1 minus Z2 term will cancel.
Okay.
It will become straight.
Okay. Let's just look. So we had what? I'm so sorry. Where were the two terms we had? We had this and this.
So Z2 minus Z1 common, so the second term there will be a minus.
Oh, and this was Z2 minus Z1. Oh, so I was saying that wrong. Oh, sorry. Where is the Z? Wait, I took.
Both phi take Z1 minus Z2 common.
1 minute. T should have a Z minus Z square. A T phi should have a square. Where is that square term coming?
Yeah, square term comes because you have 1 by Z1 minus Z3 minus 1 by Z2 minus Z3. So you add up together. So you get in the
Okay.
denominator Z1 minus Z2 and that Z1 minus Z2 cancels.
Okay. Maybe that's right. So let's see. So what do we have? Let's just do it algebraically. As I'm sorry about this. Oh, did I rub out what we needed? I'm so sorry. There was this plus 1 goes to 2, right? 1 goes to 2. Now let me just add it up and see what we get. So we get TA. Now we have phi Z1 divided by Z13 Z23 plus phi Z2 divided by Z23 Z13.
2 1.
Wait, here this was, I see, this was 2 1, and this is Z12, yeah.
Yeah, so take Z1 common.
And then we'll have two other terms which we come back to later. Okay, thank you. So that we get TA into, as you said, Z12, let's say. Thank you. So phi Z1 divided by I've taken, let's say 2 1 then, 1 3 minus phi Z2 divided by
You can take this
Z23. But we've got, let's see. You're saying this we can just substitute. But let's see, if you don't mind. So this is TA, this was Z21, right? Z21 into, and I will now a Taylor expand in 2. So one thing we get is, okay, so you say make this Z23, or just Taylor expand in 2. Just Taylor expand in 2. Phi Z1 by Z13. Okay, now you get minus phi plus Z2 minus Z1, so Z1 2 1 del Z phi Z1 divided by, and then Z, so I'll write this as Z13 plus Z21, right? Yeah, Z13 plus Z21. So I'll take Z13 out. Z13, 1 plus Z13, and Taylor expand. So this gives phi Z1 by Z13 minus phi of Z1 plus by Z13, that cancels, plus phi of Z1 times this guy with a minus sign, Z21 by Z13, and then plus and that Z21 by Z13, and there was a Z13 here. Okay, and then plus we get this by this, so Z21 del Z phi Z1 divided by Z13. And you say because we're taking 1 to 2, this can just go to 0. This can just go away. both these. Oh no.
No, no, no. This second term, third term remains, and that cancels z1.
Wait, so this is minus 5 z1,
First term and second term cancels, and
and this is z21 by z13.
there is a z1.
3 square. Wait, what is happening here?
There is dt divided by z1.
Oh, it was divided by, there was a z. Yeah, okay, excellent. And it was by z1, exactly.
Dt divided by z1 is
So this cancels, thank you. This cancels, and it also cancels here.
yes, yes.
So it's minus 5 of z13 square plus del z phi of z1, z13. With a minus sign? Z21, no, with no minus sign. Plus. Okay, something like this.
Yeah, so that's why we get square.
That's why we get square from here and nothing here. Okay. Excellent. And this whole thing is multiplying multiplying TAT. And the whole thing is multiplying TAT. Okay. So this was the term that was just those guys. I'm so sorry, people. I'm so sorry for wasting your time. Okay, but then there were the other terms. Right, there were the terms which had the explicit derivatives. There were those terms. And we have to work this out also for those terms. And in the end, we've got to then combine it all together and expand. Is it worth doing here? Let's. Okay, if somebody can read out those terms, let's finish this one calculation. I'm fine. I can do it on that board. Okay. Okay, so there was now, in addition, we have JA Z1 by Z23. And we had this guy, right? So just this. So del Z1 phi Z1 by Z21. Sorry, let me write. Del Z1 phi Z1 by Z21 times Z31 cancels with what? Is that with the denominator. Thank you. Times but we are only computing the parts that are singular.
Yes, this part is not singular as Z3 goes to Z1.
As Z3 goes to Z1. And that's the only thing of interest. Okay? So, if we've done that correctly, there's no subtlety here, right? No,
Yeah, so there is no
no singularity. As you said right at the beginning. Okay, so let's add it up now. It's a bit odd, but let's add it up. So this gives us TA, and now is this the same as phi Z3? Is this the same? Okay, so I now am going to write this in terms of Z3. So I'll write phi Z1 equal to phi Z3 plus Z13 del z phi z1 z3. Okay, was this with a minus? Was this guy with a minus? Yeah. Okay. So now this guy will cancel this guy. Because here if I change 1 and 3, the difference is regular. Okay, so this guy cancels that guy. And we get ta phi z1 phi z3 by z13, the whole thing squared. The only thing is that we should have expected to get also a derivative.
The first h time.
Yeah, and where have we missed the second term? Where have we missed the second term?
What is this? The 1 over Z12 factor sitting outside, what does that mean when we are taking 1 goes to 2 limit? Are we looking at those terms which has 1 over Z12? What do we say?
Yeah, now maybe we will also need to worry about, as Rajat pointed out, the no, but that has a k. How can that happen? Sorry, what were you saying? What were you?
There is this 1 over Z12 hanging outside.
In the parts that we of interest to us, it all cancelled. But that is possibly where I've messed up. So we got this. I think that is clean.
Why is there a minus sign?
I thought there was a minus sign because here when we Taylor expanded. Okay, so then there's a relative minus here, right? Because one of the terms came from Taylor expanding this and the other term came from Taylor expanding this. So there's a relative minus between the two. Okay, but where did I mess up on the del z part? I missed something. Give me 1 minute more. I've missed something important. Sorry, just one. 1 over z times del phi. And it should come without the TATA. So it's got a more elementary kind of place it comes from, right? Maybe that was it. You're saying the K term. No, but that had no singularity at all with Z12. No, sorry. Point again, please.
Was it 2 phi Z1 by Z13 square?
Oh. Here?
Yes. I'm just saying that in that case it will work out.
No, but you know the additional term shouldn't come with this TATA. H phi plus del z phi. It should be more elementary. Okay, H is half TATA, but how does, go on? How, I mean, if we've got something in here, it will all be multiplied by TATA, right? We want something that's not multiplied by. Yeah. Where's that coming from? Give me 1 minute. I'm really sorry about this. Where is that coming from? Just 1 minute.
Subtracting this normal order term.
Yeah.
But that didn't have a singularity.
I have seen.
Oh, that part was not didn't have a 1 goes to 3 singularity. Just 1 second. Give me 1 minute, otherwise I'll clear it up next class, but give me 1 minute. Give me one. Where was this? Somewhere I've messed up. Somewhere I've messed up. Where have I messed up? Where have I messed up? But everything. What's confusing is that everything has this TATA. Where is the source of something without the TATA? One last minute, sorry. What am I doing? What am I doing?
Should you also include the non-syntax, the first non-syntax?
But that's not universal. J with 5.
I mean, if you did JJJOP, the only way you would get this del J term would be by, so you expand first two J's first, you get another J, but when you contract like this J with the third J, you would get something like K delta AB by Z square. The analog of that calculation with phi is that you keep J phi term intact and then contract this J again.
Maybe. I see what you're saying. You're saying keep the term that was that was regular, because you're going to hit with another J. Okay, so let's see. So you're saying, suppose I had JA, Z1, Z2, and phi Z3. You're saying, let's say I do this guy first. So I will get, in addition to everything else, just jz2 pi z3 normal order. And then you do jz1 acting on this. This was A, and you say that that will give you like k by z1 phi z3. And now here if you take a derivative, expand that and you take a derivative, it might work. It might be. It might be that. Okay, since I've got so hopelessly stuck, let me try to doing the JJJ one. Maybe that's easier to do, and then we will see if it might be that what you're saying is true. It might be. That sounds like it has a good chance of working. I'm
also stuck in this calculation some days ago.
Yeah, okay. We'll do it eventually. Let us. Let us first try JJJ, and then I think maybe that it's the lesson that Harshit wants us to take. Okay, I'm so sorry, I'll try again. JA of Z1, JB of Z, let's say JA of Z2, and JC of Z3. Okay, now let's take 3 to 1. I take this quantity, everything, we're going to sum over A eventually. So this should be easier. Let's take 3 to 1, so I'll get K delta AC times Z31 times J, this, the whole thing square, plus F CAM JM of Z1 by Z31. Right, that was the term when I took this to this. And the whole thing is multiplying JA of Z2. I took 3 to 1. And then I get the same thing with JA Z1, K delta AC again, Z21, Z32, whole thing squared, plus FCAN JN of Z2 by Z32. Okay, let me check against Polchinski. Is this what he has? He has 2 K terms, 2 F terms. Must be correct, right? Okay, so that's good. Now we take 1 goes to 2. Now we take 1 goes to 2 and we do it carefully. Let's do this really carefully. Okay, so we take 1 goes to 2 and this was 2, so let's do the one where this was, sorry, 2 goes to 1. So let's do the one that there was already 1, that's easier. So that's JA of Z1. Now here what do? We take K delta AC and we'll write this as Z31 plus Z12, the whole thing square, plus FCCAN JN Z1 plus del Z JN Z1 divided by what? Divided by Z12, yes, plus Z21, okay, divided by Z31 plus Z12. Right, that's one term. And the second term was the first guy there, which was J A Z2 Z1 plus del Z21 Z J del Z J A Z1 whole multiplying K delta AC by Z31 the whole thing square plus FCA CAAM JM Z1 by Z3. Okay. So far so good. Now let us see. Now let us see. Let us now Taylor expand this quantity. So, first the 0th order term. We will get JA. Oh, now we want to do that Taylor expand. Now we want to take this. Yeah, this part is just whatever it is. Delta AC. And we will do the sum over A. So, okay, good. This part is just whatever it is, and this part is whatever it is. So, and doing the sum over A gives us KJC of Z1 KJC of Z1, okay, over Z31 plus Z12 the whole thing square plus KJC of Z1 divided by Z31 the whole thing square plus Z21. Okay, this part we can just set to 0, right? So the Z21 stuff. If from the K term, do you agree that we just get these two? Nothing else. Because we're taking 1 goes to 2, and there's nothing singular. Is this good? So we just get 2 KJC. My K parts I'm getting 2 KJC of Z1 divided by Z31 the whole thing square. Do you guys agree with this? Okay, nothing else will involve K. Now we look at the remaining terms. So this is there, and we look at the remaining terms. So we take this J with this J. Okay, so that gives us an FCAN F. I'm taking, oh, I should have just left this as 2, right? Because I just should have just left this as 2. Let 2. Because I want to take 2 to 1. Okay. So I get FCAN. Then I get FNAM. Then we get, let's first do the K term. Let's do the K term. So that's delta NA, but that's 0. Because that's FNA. So that's 0. So the K term vanishes. So then we get FNAM Z21 times JMZ1. Do you agree that this is what we get from this object? Divided by Z, and then that whole thing was divided by Z31 plus Z12. Okay, great. So we've got this term from this line. And here for this line, once again we just keep this as JAZ2 and take 2 goes to 1. I'm clearing this. Okay, so this is one term, this is the second term, then we keep this as JZ2 and take this. So we get here FCAM, then FAMN, JN of Z1, this whole thing was divided by Z31. And then because of the OP we get, this was Z2, so, and we're taking 2 to 1, so Z21. Okay, excellent. Okay, excellent. I suppose now the subtlety is this point.
Yes,
Because this has a Z21 down in the denominator, okay, we need to Taylor expand here. Okay, so this Taylor expansion, this is equal to, well, all this stuff times the leading order term is Z31, but then we have 1 minus Z12, and there's a Z21, 1 minus Z12 divided by Z31. Okay, that stuff and that stuff is similar. And presumably now these first terms cancel. Can somebody see? Minus plus. Can you see the minus and the plus? Sorry?
First term is plus and second term is minus.
No, I mean these first term and this and this cancel?
Yes, this is plus.
Can somebody see that? I'm so sorry about all this, but can somebody see that? That those,
This term is plus, right? So this upper box term.
this term was plus and this was minus? I see, this was minus and can you,
Yeah. So this term cancels. First term cancels, the second term.
first term, yeah, if somebody sees the cancellation clearly, I'm not totally able to see it. It's some 1, 2, 2, 1 kind of thing, right? Because I think it probably came from this being Z12 and that being Z21.
So this is Z21 and this is Z31. So,
But where did this minus come from?
so this is plus.
This is plus.
No, this is minus.
Ah.
But this
That one was plus. Where did this minus come from? Can somebody just remind me?
this minus comes
In the F,
Oh, in the F there is some other ordering? It's the ordering in the F. That's
ordering
right.
of the F.
Yeah, that's probably right. So we add this and this, and because of the F orderings, this term cancels, this term does not cancel, and 1, 2 goes away.
1, 2 goes away. This is a singular.
Yeah. So, but this, so there is an additional term which is Z1, Z31 the whole thing square. There is an additional term which is Z31 the whole thing square, which is like this, which is this FF.
Minus.
Okay, I have not kept track so carefully about science, but this FF.
FF gives you
Exactly. And the point here was that this FF gave us a dual Coxeter number. You remember that Casimir in adjoint representation was proportional to this dual Coxeter number. And because of that, we're going to get, I'm so sorry for the mess. Yeah, but because of that, we're going to get that this Jj on Jc, let's say this is Z and this is W, this is going to give us basically K plus G.
A plus 2K,
2K plus G, okay. 2K plus G,
so Fn is 2 times 12 Coxeter.
12 Coxeter number, okay. 2 times
Overall.
overall 2 plus A, yeah. 2K plus G times Ja of W. That is in the end the result.
Right, Z minus W.
By Z minus W, Z minus W back square. And therefore, what we will do is to take this Jc of W. Because TT with W.
No, there will be a derivative term.
There will be a derivative term, right. And okay.
If we expand,
If you expand, you'll get the W, yeah. Okay, great. So you will get this Z plus this W plus del Jc of W by Z minus W. Yeah. The important point was that this additional term came from this mechanism. That there was the Z12 and there. Okay, so the this calculation is rather clear, I think. You have to work out the details, you have to get the numbers right.
This calculation is rather clear for one reason. This J has a conformal weight 1, and that's why this PT doesn't make any sense, right? So PT overall factor.
Yeah. Okay, now Harshit, in light of this calculation, can you just retrace what you were saying?
Confused about this calculation. Why would you take, once you take the OP of JB with JC, why would you drop the JB JC term? The term with no singularity. Because if you take the OP of that operator with JB, that will have some singularity, right? That is not like some trivial.
You're saying keep this piece.
Yeah, if you take this piece.
Huh. So the piece that had a Z, that had no Z23 singularity, okay?
Yeah, that will still have a 1 by Z23 singularity when you take Z13 singularity, when you take JA with JB JC.
You know, the way we're doing the calculation, when you take Z1 with Z2, that, okay, it's true, that might have, that is the thing that will be cancelled by the, sorry, so you're worried about this and then taking this with this, right?
Yeah.
Okay. But the whole problem, since we're only keeping terms that are singular, but you're saying now this has already gone to 3. This has already gone to 3. You know, the way I'm thinking about the calculation is this. I'm right at the beginning keeping every term that is singular as either 1 goes to 3 or 2 goes to 3. This accounts for every term that is singular. All 3 points are separated. This accounts for every term that is singular as either 1 goes to 3 or 2 goes to 3. And then in the end I take 1 to 2. There should be no further singularities now between T and J, right?
But here you have, right, when you take, this is some non-trivial operator, JA with 5 is some non-trivial operator, right? And when you take any other operator towards this, it should have some singularity. I cannot drop that.
Okay, let me see. Okay, let's see. So you say that I'm looking at JAZ1, JAZ2, and JCZ3. Okay, if everything is separated, then the only singularity is when I take 1 to 3 or 2 to 3, or when this goes to this and this goes to this, this goes to this. That is correct? Clearly. Okay? Now, the way you're thinking, I think, is if I first take 2 to 3, and then I take this to that composite object, because 2 has already been put into 3 now, because we've taken that limit, that original singularity which was Z12 now transforms into a Z13, right?
Yeah.
That's how you're thinking, I think.
Yeah.
Okay? But you know, we've also got these, then we have to, to deal with those, we want to keep, then we would have to keep, take into account also the singular terms as 1 goes to 2. I think so. I think that it's correct to just think in this way, that because I'm only, you see, I'm only interested in those terms that have a singularity with this contracting with this and this contracting with this, not that, right? So I think that part is gone. Okay, so we have to work it out more carefully, but I think that's not, it does, physically doesn't seem right. Right, this calculation seems okay. I've done it very shoddily. I've not kept track of signs and factors of 2 and so on. I apologize for that. You can really easily fill it up. The key point here was this thing. But now I am confused about the Casimir, the phi thing. I will clear this up. I will clear this up next class. And let us continue for 10 minutes more. I'll clear this up next class. That's something. Let us continue for 10 more minutes. Okay. The main point was this, right? That if I was better at doing this calculation, I would have shown you that this object, which is Jj by k plus g, or maybe 2k plus g, OP with the current is what a stress tensor with the current is. I would have shown you that the same object, OP with the primary field, is what the stress tensor with the primary field is, provided H is identified with Casimir divided by k plus g. Ta divided by k plus g. Where did the k plus g come from? Because we're going to divide. We're defining T as Jj divided by k plus g. Okay, and I would have also shown you, if I was better at doing these calculations, that if you computed T with T, okay, that it behaves like a TTOP with some central charge. And I'll just quote the central charge for you, since I'm clearly hopeless at doing these calculations. Okay, I'll quote the central charge for you. The central charge is dim g times k divided by k plus g. This is, so now this g and this g are different. This is dual Coxeter number. This is group. Dimension of group times k divided by k plus g. Dimension of Lie algebra. Same number of dimension times k divided by k plus g. Okay, this dimension basically comes because you have an extra AA, sum over A. That's where the source of that is. Okay, and this k plus g comes because we were dividing by k plus g. Okay, there are 2 of those, one factor goes away, blah blah blah. Yeah, so this turns out to be the central charge of this current. 1 over z to the power 4, 1 over maybe c by 2, 2 divided by z to the power 4. This is the claim. Okay, similar kind of calculation. Actually, this calculation, the TT one, is less confusing because it's all come from JJOP. You can do it; it's not so bad. I've done it at some point. You get the answer. Okay, this one with the primary operator I will clear up in next class. I'm confused about that. Okay, now what was so? Sorry for the shortness of the lecture, but the net result of the whole thing was that if you take JA, bring them together, do the subtraction needed to make this thing regular. K by K dim G by whatever, Z12 whole thing squared. That guy has the same OP with primaries and currents and itself, as a stress tensor has with primaries, currents and itself, provided you have a certain identification of the weight of the primary. The weight of the primary is C2R divided by K plus G. By the way, we'll often use the symbol kappa for this K plus G. Yeah, kappa is K plus G. So we'll get C2r divided by kappa, maybe 2 kappa, okay, as the dimension of the primary. We'll get the OP of this object with J is just like a stress tensor with J, with the dimension 1 object, and the OP of the stress tensor with itself is just like a stress tensor. I will clear up the primary operator thing next class. The J thing we more or less see. Okay, excellent. What does this mean? This has all kinds of implications. Okay, suppose you have a theory. Suppose you have a theory with current algebra implemented, and your theory has, of course, a holomorphic stress tensor. I think we need to go. Okay, your theory also has a holomorphic stress tensor. Now, in addition to the abstract stress tensor your theory might have, we also have the stress tensor constructed by this so-called Sugawara construction. Okay? And if you have a primary field, okay, if you have, so what you have then in your theory is two objects that behave like stress tensors. Okay? So because of that, suppose I look at, I call the difference between the total stress tensor and the Sugawara stress tensor as T difference. I just call it that, because T Sugawara with T Sugawara has the form of a stress tensor with some central charge, and T total with T total has the form of some stress tensor with some other central charge. Then T difference with T difference will also have the form of a stress tensor with the difference between the central charges. Okay? So now what we have in our theory is two different stress tensors. Okay?
What would be the OP of T, this matter, and T Sugawara?
With the T difference, it will just be 0.
The OP bit of T diff with a primary field will be 0, right?
What?
I mean, just the analytic terms will be there.
Well, it depends on whether the primary field in question has the scaling dimension that we predicted or not. Okay? Suppose we've got a primary field which is in some representation R, and it has the scaling dimension we predicted. Then T diff, then the difference, then T difference with this primary field will give you 0 OP. If it was different, then it will give you the difference between HOP. Okay, I'll say this more clearly next class. But where we are going towards is the following kind of argument. Because we have independently a stress tensor, any other contribution to the stress tensor must come with a direct some kind of conformal field theory. So meaning, I can give you, let's say, a Wessumino-Witten theory, which will have the Wessumino-Witten Sugawara type stress tensor. But I could add to that theory a minimal model. Now a general primary will be a primary built out of the sigma model, and that primary will then have its dimension given by the Sugawara stress tensor. But I could multiply it with the primary from the minimal model. Okay? So then, of course, the whole primary will not have the scaling dimension that you get just from the Sugawara stress tensor. But I will give you a cleaner argument next time. But basically, the point we're going towards is this, that you've got an object which is a stress tensor. If you've got some other stress tensor, then the difference will behave like a stress tensor of a decoupled theory, a theory which has zero stress, which has 0 OP with the currents. Right, because our Sugawara stress tensor has the right OP with the currents. So this other stress tensor will have 0 OP with the currents, and therefore will commute with the part of the field theory that is responsible for building the currents. Because it will be the part that does not transform under Lie algebra.
So are you simply just adding the two theory thing to this
that is the result. That is the result. The result is this, that you see, let me say it again. I've got a stress tensor built out of Sugawara. Okay? Now this different stress tensor, whatever it is, okay, it commutes with currents. It has zero OP with currents. That's clear? Because Sugawara stress tensor makes the current transform. Come. Sorry. Sugawara stress tensor makes current transform like dimension 1 primary. Overall stress tensor makes current transform like dimension 1 primary. So the difference makes it transform like dimension 0. Okay? Now this implies then that the difference, okay, that this tells you that the current is built in, that the commutator between this difference and the current is 0. And all modes of them, yes.
So suppose I have a Sugawara construction for some Lie algebra G.
Yes.
I can look at a SU2 subalgebra of G and do the Sugawara for that.
Okay, good.
So I have two stress tensors, the total G stress tensor and SU2 stress tensor.
Excellent.
Take a difference. I don't see that this difference commutes with it.
That won't be the difference. The Sugawara for SU2 is not, I mean, for all the currents, you open with this SU2 Sugawara with no base.
But it's a good question. The question is, take the Sugawara of just the SU2. Let's say I've got SU2 inside SU3. I take the Sugawara of just the SU2 and I take the Sugawara of the whole SU3 and I look at the difference between those two. How does that work?
I mean, but will all currents behave in the same way as the Sugawara, actual Sugawara sensor?
No, but he's only focusing on the SU2s. Right? He's looking at the SU2 part of the SU3, saying under that the Sugawara for SU2. So it must then be that the Sugawara for that SU2 in the SU2 part is just identical to the Sugawara for the SU3. But you say, but that doesn't mean that other operators commuted with this. I see what you're saying. 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 You're saying that there's a different stress tensor. It's built out of other fields, but they don't commute with this.
I'm saying that it's not like a direct sum, because if you remove the SU2 from SU3, it's not a Lie algebra. SU3 is not SU2 direct sum.
I agree with that. I agree with that. I agree with that. I agree with that. Maybe I just said this wrong. Okay.
But all the currents will not have the same OP with these two stress tensors, right?
All the currents, but he's only interested in the SU2s. SU2s will.
I mean, whatever currents which transform.
No, what he's saying is, take this thing and just look at this SU2 part. He's saying build the Sugawara out of for this SU2 and look at the Sugawara for the whole thing. Now he's saying take the difference between these two. Even though the SU2 currents commute with that difference, it's not like the whole theory is built out of. I agree with the statement. Right? Yeah.
And see, representation of a current under SU2 is not the same as the representation of the current under the full algebra, right? I mean, you create two stress tensors. One for the full Lie algebra, and the other stress tensor is just for SU2, right? The transformation of a current under these two stress tensors are not the same.
Okay.
The difference won't be zero.
He makes an SU2 Sugawara.
Yeah.
He just makes it so that under that the SU2 will transform like dimension 1 by definition. right? He's just going to, it's not like he's restricting the SU3 construction to SU2. He's doing a new SU2 construction. That's what I understand from what he's saying. He's saying, okay, the theory happens to have SU3 symmetry. I forget about that. I just look at the SU2 currents and I do a Sugawara construction from that.
So restrict the sum but also divide by k plus different Coxeter.
Yeah, exactly. It's a good point. It's a good point. Maybe I said it wrong. I'll think about what you're saying. Maybe I said it wrong. Maybe I said this direct something wrong. I was thinking that the fact that the T commutes with J will make it direct sum, but you're giving a counter example. Maybe that's wrong. Okay,
One
that's
example is this compact boson, right?
What?
In compact boson, you already had this stress function, Derek stress,
yes.
right? And when you reach this cell door radius, you had an emergent SU2 symmetry. And at that point, you would have created this, you would have done this Sugawara construction to create this stress tensor.
And at that point, it was just the same stress tensor.
And that, but how could that be?
Oh, how could it be? Because one has dimension, one has charge. No, but I think it was. It was. I think it was. You know, it's just the normal free boson stress tensor.
I mean, you have something like e raised to I phi and e raised to minus I phi, and you're saying they don't contribute to this.
I mean, if you do the Sugawara construction, you take e to the power I phi, e to the power minus I phi, you do the OP, you will once again get it. It's not like this. It's not like the stress tensor of the free boson jumps at that point, right? It's just totally, it happens to be. It happens to be. So, yeah, so that actually is another counterexample to what I was saying. Right? I was saying that you take, no, maybe not, maybe not.
That is just zero. So
That's zero. Yeah. So could it be that? Okay, let me get back to you about this. Let me get back to you about this. It's a very good point, I think. I may have said it wrong. I'll clear this up. Okay, sorry, this was a disastrous lecture. I'm sorry. We'll try to do better next time.